welcome everyone to this new episode of the Water Underground Talks. Today is our great pleasure to welcome our new guest, Professor Rim Trabelsi from the National School of Engineers of Sfax in Tunisia. So welcome Rim, and thank you for being with us today.
Thank you, Viviana, for this invitation. It's a great pleasure for me to share with you my passion for investigation water resources.
Thank you, Rim. And so, talking about passion for water, do you mind telling us how did you first develop your passion for water?
Okay, it all started with my master's degree in 2003 in environmental and management science, where I joined the National School of Engineers of Sfax, in particular the Laboratory of Radioanalysis and Environment under the supervision of Professor Kamel Zouari. So this laboratory has offered for me a great place to work with perfect scientific condition and very stimulating environment for research. So within this scientific environment, I was able to develop my scientific and technical skills in the use of multidisciplinary tracer and methods to investigate water resources. Also, I had the opportunity to participate to different national and international projects. So, as Tunisia is considered to be one of the country in the Mediterranean basin, the least well endowed with water resources, all my scientific activities focuses on supporting the sustainable and the integrated resource management in Tunisia, and that's through surface and groundwater characterization and the evaluation of aquifers' vulnerability to natural and induced contaminants. So step by step, I fell in love with water resources studies, and I developed several. I developed several methods to study these resources.
Thank you. And then one more question relates to your personality. How do you think your passion or your personal interest makes you a better scientist?
Good scientist? Okay, I think that to be a good scientific, first you need to have passion. I love to read, and I like to learn more and more, and this has really helped me to develop my scientific and technical skills in multidisciplinary science like hydrochemistry, isotope hydrology, geostatistics, modeling, which are used to investigate water resources. The second thing that is important for a scientific is the perseverance. That means you never stop and you keep going. Despite the various difficulties, I am determined to continue on my way to look for the scientific evidence and the truth using new methods, new tools. Another thing that I think is very important for a good scientific is to be able to share your knowledge and methods. That means you have to be integrated in the world of scientific research by the development of cooperation and collaboration. The contact with the specialists from different research institutes and fields has presented for me a good opportunity and a qualitative improvement. That means that the collaboration has allowed me to learn new skills and new techniques that give me the possibility to develop several investigation of water resources in Tunisia.
Thank you for sharing. It's a good, also good example actually to show how you can work on your skill and help to improve or keep improving based on the skill that you have and your passion. So I think it's really important to see your example for many students worldwide. And finally, since you talked about the multidisciplinary and interdisciplinary approaches, what do you think is the impact of your work, your research outside of academia?
Okay, good question. The impact of the research is very important for a scientific because water is not only a research field, but also a vital element and a key factor for the socio-economic development of the country. That's why at the national level, I am working in close collaboration with the Regional Commissary of Agriculture Development and Water Resources. So the different research activity that I have developed are conceived according to problematic and issue that is posed by the local authorities of waters. And we try through the scientific work to give some answer to their question, such as the origin of groundwater contamination, the impact of the overexploitation, and this is very important for them to plan a sustainable management of the water resources. Another thing that is very important for a scientific is to organize some meeting and workshop with the local stakeholder, and we are in regular contact with the decision maker and stakeholder in order to translate our scientific finding to management activities and policies. At the international level, I had the opportunity for several years now to be an expert, to work as an expert and a consultant in Arabic and African countries within the framework of international project, and particularly the International Atomic Energy Project. And my task was to provide sometimes academic training and sometimes to assist them to implement water resource management project.
So I think that we are even more curious to know about your research in more detail. So if you would like to share with us your presentation, we will be very happy.
Okay, thank you. So I will talk about the salinization and recharge processes of groundwater in arid and semi-arid region in Tunisia. For this, I will start to present Tunisia. Tunisia is a small country located in the northeastern part of Africa with a total surface of 164 square kilometers. The total population of the country is about 12 million. And the climate is highly variable from humid here to semi-arid. And the big part of the country is characterized by arid to semi-arid climate. As we can see in the rainfall distribution map, that rainfall is very high in the northwestern part and could exceed 1,500 millimeters. However, in the southern part, the rainfall is very, very small and does not exceed 75 millimeters. So under such a climate, the surface water of Tunisia are limited, and they are estimated of about 2,700 million cubic meters. These resources are unequally distributed over the country. 82% of these resources are located in the northern part of the basin, 12% in the center, and the south represent only 6% of the surface water. So unfortunately, these water resources are suffering from problem of quantity and quality, which are caused by climate variability and particularly long drought period. Also, we have some natural quality degradation coming from the dissolution of saline rocks that are outcropping in the region. And we have also sometimes an anthropogenic effect and decrease of contamination. Thus, the population in Tunisia is depending more and more on groundwater as the main sources of water supply for several uses. And these groundwater also are unequally distributed over the country, and we have a quite variable quality. So these groundwater resources are estimated of about 2,000 million cubic meters. 64% of these groundwater are located in deep aquifers, which are mostly situated in the southern part of Tunisia, this arid region. And 36% of these groundwater resources are located in the shallow aquifer, which are distributed mainly in the northern and the central part of Tunisia. So these groundwater resources are highly vulnerable, and they are suffering from quantity and quality problems like the interannual and seasonal variability, which are causing groundwater level decline. Also, we have a quality degradation, such nitrate contamination and salinization, which is caused sometimes by seawater intrusion process. Under this condition, Tunisia ranks in the category of the country with the least water resource, the Mediterranean Sea. And the total renewable water resources per capita is estimated to 450 cubic meters, which is largely under the penury threshold, estimated to 1,000 cubic meters. So, the second issue that I will present today is the recharge and paleo-recharge. In fact, estimating recharge is crucial for groundwater sustainability, and such arid and semi-arid climate is very difficult to estimate these parameters due to rainfall variability. The second process that I will study today is the salinization process. In fact, this problem is affecting several aquifer systems in Tunisia, and understanding the source and the mechanism of the salinization is very important to provide further deterioration of groundwater in several places in Tunisia. So, in my different research activity, I have used the multidisciplinary methodology that is based on the tools of hydrogeology, including geology, geophysics, hydrodynamics, the tools of hydrochemistry, the measure and the trace chemical element, the isotope hydrology based on the deuterium O18, tritium C14, delta C13, also the N15 and the O15 of nitrate molecule. The methods of geostatistics and modeling, like principal component analysis, hierarchical cluster analysis, the grid gauge, the mud flow, the free flow, and recently I started to use noble gases, and particularly the long lived radionuclide, the Krypton 81 and the helium-4. So we'll start to study the recharge and paleo-recharge process in Tunisia. For this study, we have chosen 3 study areas. The first one is located in the Cape Bon Peninsula in the northeastern part of Tunisia. The second is located in the central part of Tunisia. And the third study area is covering the whole southern part of the country. All these aquifer systems are suffering from intensive exploitation, which is marked by the extinction of the spring and the decrease of the artesianism and the decrease also of the groundwater level. So this study that I am presenting now is based on review of the available data in the laboratory, the hydrogeological and hydrochemical and isotopic data that have been carried out within the research activity of the laboratory. So the isotopic signature of this groundwater system show different group. In the oxygen 18 and deuterium graph, the first group is composed by isotopically depleted groundwater with a mean isotopic composition of delta 18 of -8 per mil. Thus, this group is formed by the deep groundwater that are contained in the deep aquifer system in southern part of Tunisia, namely the continental intercalary aquifer system and the complex terminal aquifer system. The second group is formed basically by groundwater samples that are collected from the Cape Bon Peninsula in the northern part of Tunisia, and also the different aquifer system located in the central part of Tunisia. And the location of this groundwater group on the meteoric water line, the global and the local meteoric water line, traduce that the origin of these groundwater resources is mainly from the infiltration of rainwater. The third group is formed by some sample collected from the southern of Tunisia, and this group is characterized by an enriched isotopic composition, which traduce an effect of evaporation. These groundwater samples are located mainly in the short region of Tunisia. This is a depression that is filled of evaporate, and the evaporation in this part is very, very important. The tritium signature of this groundwater sample show that a big part of this sample have very, very low tritium content, less than 1%. That means that these groundwater samples are either old or there is a mixture with a big fraction of old water. That is, the recharge of this groundwater has occurred before 1950 years. The occurrence, however, some groundwater samples that are collected from the central and the Cape Bon aquifer system are characterized by tritium value that exceed 1 tritium unit, and this content traduces the occurrence of water of modern infiltration, particularly in the outcropping area of the Miocene and Oligocene formation in the Cape Bon and the central part of Tunisia. We'll move now to C14 signature. Here we have the map of the Cape Bon Peninsula, and we can see that a big part of the collected groundwater sample are characterized by very high C14 content, which means that there is an effective and active recharge of this groundwater system. However, in the central part of Tunisia, we can see that there is a gradual decrease of the C14 activities from the northwestern part toward the south and the east. That means that here we have a gradual decrease according to groundwater flow path from the recharge area located in the western of the basin toward the discharge area located in the southeastern part of the basin. However, the spatial distribution map of the C14 show that a big part of the collected samples have C14 activity that is less than 20%. That means that a big part of this aquifer is very, very old. That is confirmed by very low tritium content, also by the depleted isotope stable isotope composition, and that means that this groundwater are fossil and not renewable water. The local recharge and the active recharge is located in very, very small area that are scattered along throughout over the southern part of Tunisia. So big part, as I said, of this groundwater are very old and exceed the datation limit by C14. That's why to make to date this groundwater, we have used another tracer. The Krypton 81 is a new tracer. And the estimated age using this tracer range between 150,000 years to 600,000 years before present. Now we can see the spatial distribution map. This is the youngest groundwater sample located in the recharge area, and we have here the old groundwater which are located through the short region. So here we have very important data that should be introduced to the modeling, to the models that are used for a sustainable management tool by local local authorities. And this confirmed that the exploited groundwater in southern Tunisia is very, very old. It's fossil water, non-renewable. We have only small recharge, and we should be careful when managing these groundwater resources. And using the Krypton 81H, we have been able to calculate the groundwater velocity, which is very, very slow, does not exceed 1.5 meters per year. And this gives the time for the water rock interaction process. Now we go for the second topic, the salinization process. We have two case studies, one in the coastal area and the second one in the continental region. So here we have the two study area, the Shigafia Basin in the central part of Tunisia and the Chafara Basin located in the eastern part of Tunisia. So the Shigafia Basin, in fact, is a small basin. Here is located 20 kilometers to the west of Kirwan. This basin is characterized also by semi-arid climate. And we will study the shallow aquifer of this basin, which is lodged in the quaternary deposits. The piezometric map of this aquifer show that we have groundwater flowing from the northwest toward the southeast. So the recharge area are located in these mountains, and the groundwater is flowing towards this fault. And here, what we can distinguish, here we have some depression, that's some sapra. As I said before, the sapra is depression that is filled with some evaporate and salty rocks. And you can see here that there is a flow line from this sapra toward this southern part of the aquifer. In parallel, the groundwater salinity map show that all the collected samples that are located in the recharge area are characterized by very low salinity, which not exceed 1 gram per liter. However, this salinity is increasing toward the southern part, near to the Sabha, and also in the southern part in the Sidi Abdallah region here. The application of isotope tracer has allowed also to identify a different group. In the graph 018 deuterium, we can see here there is two groups. The first group is located on the global and the local meteoric water line, which reduce rapid infiltration of rainwater. And the second group is located according to the mixing line between groundwater and Sabha groundwater. And this confirms that this Sabha is contaminating the aquifer system, and that's causing the increase of salinity. So the use of chloride 018 graph also has confirmed this relationship, has confirmed the presence of the mixing between groundwater and the Sabha groundwater. And also it has highlighted the presence of an evaporation process. Using stable isotope mass balance, we have been able to quantify the sea intrusion rate, which range between 3 to 9%. And we can see in this graph that the seawater intrusion rate is increasing with depth. That means the evolution of the saltwater freshwater interface seems to be controlled by the distance to the Sabha, also by the hydraulic gradient. Now we can move to the second case study for the salinization process. This is the Jafara region located in the southeastern part of Tunisia. In fact, this is a plain which represents a multi-layer aquifer system that is shared between Tunisia and Libya. So this region is characterized also by semi-arid climate, with total rainfall which not exceed 200 millimeters per year. So in this study, we focus on the shallow aquifer, which is lodged in the quaternary alluvial and detrital levels, the sand and clay sand of the Miocene, especially in the coastal fringe. Here we can see the map of the hydraulic head, and you can see that the recharge of the aquifer is located in the western part of the basin, and the groundwater is flowing towards the Mediterranean Sea. Here, near the coastal area, we can see the migration of the line, the ECPs0 towards the continent. And here we can find also some negative value. That means we can cause here an inversion of the hydraulic head, and this region are highly vulnerable to seawater intrusion. In parallel, the spatial distribution map of the salinity show that very high value of salinity are located in the coastal region, and the salinity could exceed 10 grams per liters. And this is very, very high. And you can see here sometimes that exceeds 20 grams per liters. So in the case study, you have used a different tracer. And here we can see the chemical tracer, the Piper diagram. We show that there is an evolution of the chemical type from the sulfate sodium type to the chloride sodium type, which characterizing the sea water. Also, the different binary diagram, the sodium chloride, the bromide chloride, also the ratio magnesium, calcium, sulfate chloride, all confirm the existence of the mixing with the sea water. This relationship has been confirmed also using the oxygen 18 and deuterium. And you can see here in this graph, there is a mixing line between the groundwater sample of the Jaffa aquifer system and the seawater of the Mediterranean Sea. Also, we can distinguish a small slight evaporation that is affecting the groundwater system. This tendency are also confirmed by the graph chloride oxygen 18, and we can see here different the mixed line with the seawater and the evaporation line. So using a stable isotope mass balance, we have been able to quantify the seawater intrusion rate, which range between 0 and 14. And the most affected area are in the region where we have recorded a very high value of salinity. And that confirms that the principal process that affect or that cause the desalinization of this aquifer is the seawater intrusion. So the direct impact of this study of salinization is to reduce pumping in this region, to establish a groundwater management plan in the most vulnerable area, and to examine the possibilities of artificial recharge in most affected area by saltwater intrusion. So with this, I will finish. I thank you for your attention. Just last word. I would say that research is rarely done alone, and I would like to thank all my colleagues, my co-authors, and my collaborator who allow me to develop different research investigation. And thank you.
So thank you very much, Rim, for sharing this very presentation that allowed us to travel within Tunisia, but also in the different application and use of isotopes. I think it provides a lot of insights. So thank you so much for sharing your work and your research with us.
Okay, thank you.